3.2 is basically mainly, looking into mean value theorem. So in this sections, what we're going to do is we're going to mainly look at two theorems. The first one is a Rolle's theorem. And the reason why we need to look at Rolle's theorem is basically the proof of mean value theorem is basically started from this Rolle's theorem. Right? We use Rolle's theorem to prove mean value theorem. And mean value theorems were used to prove the other theorems later on that we're going to look at. So once again, I'm not going to be going back and then proving of this theorem because both Rolle's theorem and mean value theorems are proved in your textbook, so you can look at it and study out of it. Right? What we are interested in right here is being able to use Rolle's theorems and mean value theorems, meaning we need to clearly understand and remember what are the criteria that need to be met so that I can use the conclusions of the Rolle's theorem, or what are the criteria of the mean value theorem that I need to check to use the conclusions of the mean value theorems to continue on the problems. Okay. And another thing is how to, I mentioned about all the way in the beginning of the semester, we will be mainly looking at two types of proof. One is the direct proof, and then one is proof by contradiction. Right? We're gonna learn those two. So the direct proof, we already learn that when we are doing delta epsilon proof. Okay, so we go from the if statements and then go to then statement using the direct proof, going one directions. So in this sections, what we're gonna do is we're gonna learn how to use the proof by contradiction. Okay, so that's an overview of this sections, right? What we're gonna do. So the first part is what is a Rolle's theorem? That's what we want to look at it. Okay. The Rolle's theorem basically say that if the functions have these three criteria meet, then we can use the conclusions of it. So what are the three criteria? The first one is function must be continuous on a closed interval, and the function must be differentiable on the open interval, because we already know that at the endpoints function is not differentiable, right? And then lastly, the endpoint, right? The function value at the endpoints, they must be exactly the same. So if these three criteria are met, then this Rolle's theorem guarantees that there will be at least one number between this interval a and b such that f prime of c will be equal to 0. So here's a few cases that I gave it to you with the graphical approach. You can see that if a function is a constant function, okay, f of x is equal to, let's say, a number 3. So this is 3 right here, and this is a constant function, which is a horizontal line. So if it is a horizontal line between a and b, right, then we know that it is continuous on a closed interval and differentiable on a open interval. And then notice that the endpoint f of a and f of b, they are the same value, right? They are equal value. So these three criteria right away met for this Rolle's theorem. So what basically Rolle's theorem guarantee that is there will be at least one number c between this a and b such that f prime of c, that will be equal to 0. So you can look at it right here. A tangent line will be a horizontal tangent line. So f prime of c, that's basically talking about a horizontal slope of the tangent line at that particular point is 0. That basically means that we're gonna have a horizontal tangent line like that. So you can see that for this particular first case, the constant function is a horizontal tangent line every point, because it's a horizontal line anyway to begin with. And the other one, you can see that there may be one peak, right? There may be one horizontal tangent line involved. Notice that again, the criteria met is continuous in the closed interval, differentiable everywhere in that open interval, and the endpoint are the same value, right? The function value at the endpoints, they are the same. So that tells us there will be at least one number c such that f prime of c will be 0. Are we all okay with this so far? And the other two cases basically what, there are as many loops as I can have in between A and B, as long as if f of A and f of B is the same at the end, and then also the function is continuous and differentiable everywhere in between them, then we will have what? This case is more than one C that gives us f prime of C is equal to 0. So that's basically what the Rolle's theorem is like, pointing it out to us. Right? So the Rolle's theorem basically like, guarantee situations. Any questions before I move any further from here? All right. So what we want to do next is like basically checking how to apply this Rolle's theorem. So the first function is given to you, f of x is equal to x squared minus 5x plus 4 on the closed interval of 1 to 4. Right? And what we want to find out is find out all the number C such that it satisfies the conclusions of Rolle's theorem. So for the part A, I know that the function is continuous on that interval because it is a polynomial function, right, by theorems that we learned before. And f is differentiable everywhere on polynomial functions on an open interval 1 and 4. So the last thing that I need to check is the endpoint function value, are they the same or not? So I plug it in 1 into the functions that give me 0, and I plug in 4 into the functions that give me also 0. So that basically helped me to get what? The third criterion met, which is f of 1 equal to f of 4, which is the endpoints are equal to each other. So because of these three criteria met, then I can basically say that by Rolle's theorem, right, there exists a number C on this open interval 1 through 4, such that I can definitely get, right, f prime of C is equal to 0. So means there will be at least one peak in that interval. Okay? So to find out those values C, what I do is what? I take the derivative of the function, which will become 2x minus 5, and then solve for, set that function equal to 0 and solve for it, which will give me what? X is equal to 5 over 2. Okay. So that basically gonna give me what? The peak. Okay. Now, does it make sense? All right. With what we learned before. If you look at this function, the function is a quadratic function. So quadratic functions, we know that it's only have the peak, which is the maximum point or the minimum point, because if it's opening upward, it will be minimum, and opening downward will be maximum. We know that, right? This is opening upward. So where is the vertex? That's what we need to look at it. All right. And since this 5 minus x is equal 5 over 2 equal to x is in this interval, then we talk about what is satisfied on this. Okay? So you always need to check with the interval also, okay? With the Rolle's theorem. Are we all okay with this? Any questions before I move on? Right. So on the second example, again, once you find out, any number C in the interval of -1 and 1 that satisfy the conclusions of Rolle's theorem. So first thing, when I look at this function, right, function g, the domain is everything except what? 0. Since the interval that we are looking for is in a closed interval of -1 to 1, that includes something that is not in the domain of the function. Right away, that tells me, all right, the function g does not define at 0, which is in that interval that we are looking at. That basically right away tells me the function g is not continuous functions, because in order to be continuous, the function must define and the limit must exist. Okay? So the function does not define, so it's automatically known that it's what? Not even a continuous function. So because of the criteria, the first criteria that we need to check fails, the Rolle's theorem is not applicable for this particular interval with this function. Are we all okay with this? Any questions? Okay. So the next one, when you look at it, h of x is equal to absolute value of x in the interval of, again, -1 to 1. And we know that absolute value is a continuous everywhere, right? So it is continuous between -1 and 1 also. So that's good. But however, from the past, we already know that h is not differentiable, right? The function is not differentiable at when x is equal to 0, which is inside the domain that we are looking at, right? Interval the domain that we're looking at. So since it is not differentiable at every point on this domain, then the Rolle's theorem does not apply, right? It's not applicable in this case again. So that's our conclusions right here. So you really need to know how to check the criteria of a Rolle's theorem so that you can talk about the conclusion of it. So this is like an if-then statement, right? On the if part, you need to check 3 criteria. And only all those 3 met, then you can talk about then part. Any questions before I move any further? Right. So this is a computational part of it. And the next part that we want to look at is basically, how to use the Rolle's theorem in a proof by contradictions idea. So we will be looking at like the kind of problems that we did before in the past, right? We want to show that in the past, we want to show that an equations, the given equation has what? Solutions or not. But this time, okay, we want to show that a given equation has exactly one solution. So how do I talk about exactly one? Right? You cannot use the IVT, intermediate value theorem, that we learned before, because IVT only talk about the existence. It cannot tell you uniqueness, nor how to solve for it, right? How to find it out. We know how to solve those polynomial functions, but I'm talking about like in general for other different cases that we don't know how to solve. Okay? So again, intermediate value theorems basically say that if the criteria meets, then we can guarantee that there will be at least one value. So for now, we want to talk about what exactly one. So how do we prove that? Okay, so that we need to be able to look at, right, the structure of proof by contradictions. And make sure you stop me on any part of this logic that you don't get, okay? The proof by contradictions, the logic is this. We know what we want to prove. So what we're going to do is we're going to start with a wrong assumption, okay? We're going to start with a wrong assumption, which will incorporate it into the theorems or the axiom or the theorems or corollaries that we already know that always going to be true. So along the way of like working out the process of the problem, and we will be able to find out, or we are trying to look for, a contradictions. Okay? And once we get the contradiction, that basically tell that the theorem is already proven to be true. So therefore, the only one, right? The only one that could go wrong is our assumptions. Since the assumption that we make is wrong, the other must be true, which is something that we want to prove. Okay? Which is something that we want to prove. So, for this particular problem, okay, we are trying to prove what? A polynomial equation with third degree. So when we talk about the third degree from the pre-calc, we know that the graph of this third degree can be at least having what? 3, 0. That's one situation. 1, 2, 3, right? It could have 3 zeros. Or it could have these situations. Going up and then come back down and touch it and then go back up, which is the multiplicity of 0 right here is 2. So therefore, we will only see 2 zeros. Or the last one that we can have is what? We only have 1 0. So it means I go across it, come back down, and go back up. It never touch it again. So we only have 1 0. Right? And that basically tells me I have one real 0 and I have what? 2 complex zeros. This is not 0. Right? 2 complex zeros such that it will never touch the x-axis again. So we may have like these 3 cases. But how do we prove that this given equation is only having 1 0? And that's why we need to use this proof by contradictions idea. Do we all see the picture before I move on? Okay, so how are we gonna move, how are we gonna use this, like, these steps that we talked about right here? We wanna prove this case, right? So what we can do is we can make the wrong assumptions of saying that, let's say I have 2 zeros on this equations, right? And then using, this wrong assumptions into the known theorem that is already proven is always true. And we want to find out there is some contradictions along the way. Because, right, there is a contradictions and the theorem that we're using is already proving always true. The only assumption that we can, the only thing that it can go wrong is the assumption of having what? 2 zeros. Okay. So if you cannot have 2 0, that means you cannot have 3 0, or you cannot have 4 0, not even mention 4 0 because this is a third power, so you cannot have 3 0. So therefore, only thing left off is what? You're only gonna have what? 1 zeros. So that's the idea, that's the picture and the logic behind of it. Any questions before I move into writing part? Because you need to understand this proof by contradictions idea first before we can start writing it step by step. Otherwise, what's going to happen is you're going to be memorizing what I'm writing down. Okay? And then from there on, you're going to be like,
What is number 4?
Oh, number 4 is the conclusions.
Okay.
Okay. The conclusions of because of like this, if there's a contradictions, the only thing that it could make, it could go wrong is false is what? The assumption, right?
Mm-hmm.
So because of the assumption that we make is a false statement, so therefore what we want to prove is what? True. So the 4th step is the conclusion of, now we can say that what we want to prove is true. Okay?
Mm-hmm.
Are we all found so far? You got the logic, right?
Yes.
Okay. So let's. Are we all okay with this? Once again, you will feel, it is normal that you feel like overwhelmed and then you feel like, oh shit. Hopefully you're not recording. Sorry. Right? Oh crap, Because this will be probably the first time you've seen this, proof by contradictions idea. Yeah? So let's take a look at on the actual part of writing. So keep in mind that the whole picture that I gave it to you, right? So first, what I'm gonna do is I'm gonna be like stating the left side of the expressions on the left side of equations as in function notations. So therefore, the equation is basically talking about finding the 0 of the function. because the theorem is going with the functions, right? Continuous functions and differential functions, not an equation. So that's why the first step I'm trying to renaming it. So I will say that let f of x be equal to 2x to the third plus 3x squared plus 6x equal to 6x plus 1. Now I can see that this is a polynomial function, therefore it is continuous, that meet the first criteria of the Rolle's theorem. And then we know that polynomial functions are differentiable everywhere. So that meets the second criteria of it. But what we don't know and what we don't want to spend time and find out is the third criteria, where the functions on a closed interval, the endpoints are the same, because the function never tells where the closed interval is. And you don't want to find out any value that's closed interval either, because the closed interval that you're talking about, it might not include the zeros. Okay? So therefore, this is how we approach with the assumption that we're going to make. So assume that, remember, we are trying to prove that there is exactly 1 0. So now we can assume that the function has 2 real roots, which means 2 real zeros, such that the first 0 C1 is less than the second 0 C2 in a numerical order. So you need to indicate that, so that when you write it on later on, it will be like easier to write it. So what this basically mean, what this assumption basically mean, that help us to meet the third criteria of the Rolle's theorem, which is f of C1, and the value of f of C1 must be equal to the value of f of C2, because both of them are what? The zero of the function, so the function value will be always equal to 0. Are we all okay with this so far? Is there any questions before I move any further? So do you see now that what I mentioned earlier, how do we incorporate our assumption into the theorem that is always going to be true already? Are we all okay with this? So now, because of this 3 criteria met, by Rolle's theorem, this is guaranteed. There exists a number W such that the number W must be between what? This n two endpoints, right? Meaning in this case 2 zeros that we assume in, which is C sub 1, between C sub 1 and C sub 2, such that the derivative of the functions evaluating at W will be equal to 0. That is basically what the Rolle's theorem guarantees. Right? Now, to make it more precise, that would be what exists at least, right? A number W, because it could be more than 1. We just don't know. So now, when we look at right here, I particularly only write down 1 because if there is 2 0, then it should have only 1 peak between those 2 0, right? So now, when we look at it, f prime of x, that will give me 6x squared plus 6x plus 6. And we set it equal to 0 for that function to find out the w. And what we found out is a quadratic equation that is not factorable. So if I put it into quadratic formula, that ended up in a complex solution. So that means our w is a complex number, which the Rolle's theorem is basically talking about in a real number sense. So another way of saying is, this is the contradictions that we find right here. Okay? The complex number part is the contradiction that we found right here. Any questions before I move any further from here? So another way of saying is that we don't find any w at all. Okay? We don't find any w at all. Are we all okay with this? So if you want to make it a little bit more precise on writing, you might probably want to put it like this. Instead of x, put this w, because I want to just put it in general. So W and W. Right here is W, because we are solving for W, right? And such that this will become what? So W is a complex number. So that basically indicate that, right? This gives us a contradictions of f prime of W equal to 0, right? F prime of W equal to 0. Have you all found so far? All right. So now, what does this mean? We found out the contradictions. That basically means the contradictions, okay? The only thing that it could go wrong is it will be contradicting with what the assumption that we make, because the theorem is a true theorem, right? The only thing that we incorporate into the theorem is the assumption that we make, right? Since it's giving me a contradiction, therefore there will be what? Contradicting that assumption that we make is true, right? That basically tells me that equations cannot have two real zero, because our assumption is wrong. So the equations cannot have two zeros. So therefore, if the equation cannot have two zeros, then it will only left to say that in this polynomial equations, right, we only can have what? Exactly 1 0. So that's the end of it. Questions, difficulties on this proof? Are we all okay with this? All right. If you're okay with it, then we're gonna move on. Okay. And I'm skipping this next example. You can basically try it out. And how do we show that there's at most two zeros? We're gonna look at into this case. When we want to show that there's at most two zeros, we're gonna say that our assumption will be what? There's 3 zeros. Because if I can show that there is a contradiction with this 3 zeros, then I only left to say that with this polynomial function can have what? Either 2 0 or 1 0. That basically means at most 2. Right? So you can apply the same structure, but you need to be careful on the writing part on that. Because if you say that there is 3 0, what's going to happen is on this point, okay, at this point, you're going to have not only 1W, you're going to have 2W. And those 2W will be trapped between the zeros of the function that you talk about. Okay? So take a look at on the picture that I drew it to get an idea. If you have 3 0, that means what? You're going to have one peak right here, that's your W1. And you have another peak right here, that's W2. And those W's are trapped between these 3 zeros. So you're going to have to write it down like, C sub 1 is less than W1, less than C sub 2. And another one is C sub 2 is less than W sub 2, less than C sub 3. So it will become a two inequality that you need to write it. Okay? So that's basically the idea of writing on that part, and then the rest will come the same thing.